recording and get into it. So today we've got the second part. Oh, and now I have no navigation if that's up here. Maybe that wasn't the best choice. Today we have the second part of the atom probe lecture, and today what we're going to look into is atom probe instrumentation. Typically, when you go to conferences and you see people presenting atom probe results, very often it's very much application driven. So people don't necessarily concern themselves very much with the limits of the instrumentation, the detection system, and so on. But I think it's very important to understand the instrumentation before we go to the field evaporation physics part, so that you know what data we actually get and what the implications are and what we know and what we don't know. Because obviously there's things because of the limitations of instrumentation, we can't possibly know, and there are things we do know. And so today what we're going to look into is overview of an atom probe. What does the instrumentation actually look like? And last week we already talked about our boundary conditions are that we are sort of have 20 to 80 Kelvin temperature, and we have a pressure of around 10 to the minus 10 to 10 to the minus 11 millibars. Here in Erlangen, we're even one order of magnitude below that, but this is sort of the general vacuum level we work at. This sort of sets the general stage of what the instrument looks like. And you've already seen the atom probes downstairs, and most of what you see is actually the vacuum system, and the vacuum and the cooling system that really dominates the appearance of the instrumentation. And so we're going to look into UHV generation and practice. So what is important about it, and why is ultra-high vacuum a bit different than regular vacuum? Because we're talking not about sort of the pressures we have, but residual contamination is really the important bit. Then we're going to talk about the technology. And very important for us are microchannel plates and delay line detectors, because this is essentially what all modern atom probe instrumentation uses for detection. And then we're going to look into how voltage pulsing works and how laser pulsing works. And here, voltage pulsing is a little bit more, we're going to look a little bit more into that because it involves a little bit more engineering, there are more boundary conditions, and laser pulsing is a little bit more straightforward from the engineering side. Maybe I'll think about that differently in about 2 weeks when we get our first laser that we'll build ourselves, but we'll see. And we already have, okay. Then we'll have to make sure that Mr. Kostwein can hear us. And we have, oh. Is it working now? Can you hear us now? Okay. Good. So, yeah. Laser pulsing is a challenge we still got ahead of us, but during the course of this semester, you'll experience live how a new laser system is built. Okay, so this is the general layout of a local electrode atom probe, and this is really the dominating type of atom probe that's out there. There's been a bunch of different acquisitions and mergers over time. Before Kamika, which is the current, or Imago as it was called at the time, was the dominant seller of atom probes. There were a couple of different ones. And at the end of the lecture, I'll go and get a atom probe stage. So essentially the part where everything happens from an older atom probe and one from Oxford Nanoscience that I have lying around in my office, so that you can see what things looked like before. And this is an atom probe that's been used for 15 years, so definitely works well. and is also the one that the reflectron, so high mass spectral resolution, was first implemented in, that we'll talk about at the end of the lecture. So this is one of the early ones, 2004, and the reason why I took that one is because it's the simplest sketch that's possible, and the parts that we have is essentially a 3-stage vacuum system. So we have a load lock chamber where the pressure goes from 1 bar down to about 10 to the minus 6, 10 to the minus 7, 10 to the minus 8 millibar. Yeah? So you put your specimen in there, and then it goes from ambient pressure to round about this pressure. Then we have a buffer chamber. Yeah? You can then move your specimens into the buffer chamber where they reside at the pressure of about 10 to the minus 9 millibars. Again, it's instrument specific. On the LEAPS, it's about 10 to the minus 9s. On our home-built ones, it's about 10 to the minus 10. The main purpose of having this is to facilitate a continuous movement of specimens. So you want to utilize your instrument continuously. So in order to have a continuous movement of specimens, you have a buffer chamber so they can move some out and some in without always having to go to air. Because this, going from 1 bar to 10 to the minus 8, will take at least about 3 hours. But realistically 12 plus hours until we're at the bottom pressure. And what happens here is something we're gonna talk about in the, later in the lecture, is a desorption of water vapor. So if you open something to atmosphere, a monolayer of water vapor will form on the surface, and this monolayer will slowly evaporate. If we heat up to high temperature, it will evaporate faster, but at room temperature, it can take a little while. And then we'll get to 10 to the minus 8 millibar, here 10 to the minus 9 millibar. And in the analysis chamber, we have 10 to the minus 11 millibar, roughly. And so we have different pumps. Here we've got turbo pumps, which you can see here. This is a turbo pump. Here you don't see it underneath. It's the same turbo pump. Oh no, sorry, it's not underneath. It's back here, the same turbo pump. And here we've got an ion getter pump. We'll also talk about that one. So there's a couple of different ways to set up a vacuum system to achieve that. Here's an ion getter pump. It's big and heavy, but very powerful. It can pump any kind of contamination you have. In our systems, we use non-evaporative getter pumps. We'll talk about those as well. They have the upside that they're much smaller for the same amount of pumping power, but they pump relatively selectively, so you need to keep your system a little bit cleaner in order to use them, but it makes everything a lot lighter. Here we've got the detector. The detector is flanged on here, and the specimen sits somewhere in here, and the ion fly towards here. And then we've got a detector here with the electronics. So here we've got the various attachments for the delay line detector, high voltage power supply, and so on, and we'll talk about that later on. But this is sort of the basic layout that pretty much most systems will follow. Oh, and one thing I forgot, here we've got the cryostat. So here we've got a Gifford-McMahon cryostat. We'll talk a little bit about what those cryostats are as well. So essentially, it's a closed cycle helium system, helium piston system that allows us to cool our specimens down to the temperature we want them to. So the bottom out temperature of these systems is typically around 4 to 10 Kelvin or 2 to 10 Kelvin. But due to losses in transmission of the cooling power, we don't get down to those levels. We get down to about 20 Kelvin, which for atom probe is more than good enough. And there was a study not long ago where people tried to go even lower, and they found out that nothing interesting really happens below 20 Kelvin. So yeah, that's it. Okay, so this is the basic layout, and we're going to talk about the individual components, starting with the vacuum system, because it's the all-encompassing system that we see here. Then we'll talk about the cooling system, how we can cool, how we can measure the temperature, how we can measure the pressure, and what we know and what we don't know about it, what the vacuum chamber is about, because you see the vacuum chamber is also not like a regular vacuum chamber you know from your SEM or any low vacuum systems. It's an ultra-high vacuum system, meaning everything is completely made from metal, so that we can heat it up to high temperatures, somewhere between 120 and 150 degrees C. so that we get fast desorption of water vapor and we can get a very clean system. Yeah, we call that baking, and we'll get to that. And lastly, we talk about the detection system, pulsing system, and so on. Okay, so let's start with the vacuum system. And the vacuum system, in vacuum systems we can have different vacuum levels, and we call them rough vacuum, medium vacuum, high vacuum, and ultra high vacuum. And these are more or less arbitrary limits. They're more or less arbitrary limits, but they have some system to them. As a rough vacuum means typically we can use mechanical pumps to establish that vacuum. We can usually establish that vacuum through pumps. So 1 hectopascal is around 1 millibar, so 10 to the 0 millibars would be 10 to the 2 pascals. So everything here is in SI units in pascals, but most people will talk about millibar or torr, and torr and millibar are sort of kind of equivalent. 730 torr is one bar, but we're talking about orders of magnitudes that are very similar. So just remember that this is 10 to the 0 millibars. And this is something you can easily reach with mechanical pumps. This is why it's called a rough vacuum, because we're using roughing pumps for that. Then we have a medium vacuum that goes down to around 10 to the minus 3. And this is something we can reach with oil-sealed pumps. Oil-sealed pumps. Then we have high vacuum, up to around 10 to the minus 7 millibars, or 10 to the minus 5 hectopascals. We can reach that one with turbopumps, and we can reach that without baking the system, so without heating up the system, which means we can use rubber, we can use other polymers pretty easily, polymers that only can withstand room temperature. And then we have ultra-high vacuum systems, and ultra-high vacuum systems means we have we have usually ion pumps or sorption pumps. They're no longer pumps that get rid of the gases, but pumps that trap the gases. So some kind of sorption pumps plus a bakeable system. So the system is more or less sealed from the outside, because we can't closed from the outside, because we can't use any regular seals that would allow for any motion. Just for example, if you think about the SEM, then you have some detectors where there's an O-ring and something is some rod is in the O-ring and you can move it in and out. The vacuum will get a little bit worse for a short amount of time, but apart from that, it seals pretty well. This is no longer possible at these vacuum levels. If we want to have any motion inside, typically what we need is some magnetically coupled devices. So we have some magnets that move something inside by coupling it through some wall. And we have sorption pumps, bakeable, and a bakeable system. And typically, if we look at what we do, field ion microscopy and atom probe tomography, so field ion microscopy sort of lives in the base pressure already in the ultra-high vacuum. I think it would be possible to make a field ion microscope based on non-ultra-high vacuum components, but it would be a bit less practical. And atom probe tomography, or atom probe definitely need ultra-high vacuum systems, and this is why we're going to look at ultra-high vacuum systems. But we're not going to forget about rough, medium, and high vacuum, because in order to establish an ultra-high vacuum, we need to go through a rough, medium, and high vacuum to get to the ultra-high vacuum. And we do not necessarily have pumps that can go, we neither have pumps, nor do we have measurement devices that work through all orders of magnitude. There's no single pump that can get you from rough vacuum to ultra-high vacuum. And there's no single measurement device that can allow you to measure from rough vacuum to ultra-high vacuum. And this is why we still have to look at rough, medium, and high vacuum when we get to the ultra-high vacuum. But we're not alone. So we have particle accelerator people that use the same techniques. We especially have people doing surface studies. And there's quite a few of them here in Erlangen, especially at chemistry and chemical engineering. There's quite a few people that have ultra-high vacuum systems for surface studies, because in the end, what we do in atom probe tomography is also surface studies. We remove atoms from surfaces. And of course, the big bias in that area is semiconductor processing. So very often, if you want to understand what equipment you have available and why you can't get your hands on certain components at certain amounts of time, it's important to look at semiconductor processing, because there you have equipment that also goes down into the ultra-high vacuum, range. Yep.
The increase in the temperature in the ultra-high vacuum is just because of the kind of pumps that we use in there, or if we want to go, for example, if the pumps which are currently used for high vacuum are advanced, and in the future, for example, we can use them for ultra-high vacuum, then we will not have the increase in the temperature, or if we
the increase in so in ultra high vacuum equipment, we need to go to elevated temperatures to desorb all the water vapor and other contaminants that we introduced from opening the system. So if you build the system originally, or you have to do some maintenance, you need to open the system to atmosphere, and this will introduce water vapor and potentially also other contaminants like hydrocarbons. So how to get rid of them has no impact, or the type of pumping doesn't really have an impact on the speed of desorption, because this is just a desorption from the chamber walls into the inside of the chamber. And this is why we're heating up. That's independent of the type of pumping that we're using. And by the way, there's people that are going even further, but this is sort of the best vacuum systems that are available for, or the cleanest vacuum systems available that are open systems. Open systems meaning that I can introduce a specimen. There's people that go down to 10 to the minus 17, but there are people, for example, building atomic clocks. So you build a clock, you close it up, you clean it as much as you can, and then you never open it ever again. But for us, of course, we need to introduce specimens, so we don't have that luxury. Okay, so for us, the important bit is now what contaminants can we have, which contaminants do give us problems, and how to get rid of them. And this is what we talked about right now. This is the whole heating issue. Yeah. So, and the important thing for us is the vapor pressure. Yeah. So what vapor pressure? Here again in pascals, so 10 to the minus 8 means 10 to the minus 10 millibars. Yeah? So this is at the end roughly where we want to end up at, versus temperature. And you can already see that things like helium, hydrogen, neon, and so on, they all have equilibrium pressures that are so high at these temperatures that they will just immediately desorb anyway. So if you pump something down and you have some residual helium, no residual helium will adhere to your surface. And similar things for oxygen, methane, argon, CO, CO2. But for hydrogen, if you look at hydrogen, if you look at water vapor at 300 Kelvin, where we're at, then we already have a much lower equilibrium water vapor pressure. But this is, of course, for bulk water. We are now thinking about water adsorbed on surfaces, so things look a little bit different. But this sort of gives you a rough tendency. Which gases you don't have to worry about? Helium, definitely you don't have to worry about. Helium, hydrogen, neon, at least as introduced originally. We'll talk about hydrogen separately, because this is the last contaminant to go usually. And the reason for that is that we usually use stainless steel chambers, and the hydrogen comes out of the stainless steel chamber. But essentially, the further up we go from here, the worse our contaminants get. And you can imagine what's probably worse than H2O. I mean, these are all surface-sorbing species. So the larger the molecule, probably the less it will want to dissolve, because we're mostly talking about van der Waals forces. So H2O is bad, but but hydrocarbons, if you have any oils, for example, then it gets even way worse, because they want to evaporate even less. Okay, and so the question for us is, how long does it take to get rid of them? So always remember, addoprobe pressure is about 10 to the minus 12 pascals. And so how long would it take for molecules with a certain desorption energy to desorb to desorb from the surface. And so you can see that we have maxima here. So essentially we have got two parts. We've got two parts, and this part here is kinetically limited. Yeah. This is kinetically limited, means we get desorption of the molecules, and it will take a certain amount of time. This is the time to reach a certain pressure if I have one monolayer adsorbed on a surface. Whereas here on this side here, we are energetically limited. We're energetically limited, so essentially if the desorption energy is higher than a certain energy, then the molecules just sit stable on the surface. So if you have very heavy contaminants, then what will happen is that they might not even desorb just because the desorption energy would be too high. But now if you're saying, okay, then I can just leave some oil in my ultra-high vacuum chamber and it will be fine. No, it won't, because you will always have some cosmic radiation. You will always have some processes by which these molecules decay into smaller fragments, and they will then start desorbing. When we are downstairs in the lab later in the lecture, you will see that cosmic radiation is everywhere, and we see it in our detection systems quite a lot. And so we would have a pretty large amount of molecules desorbing just because of decay issues. And so what you can see is that based on the pressures we're after, so 10 to the minus 8 pascals. Was I the wrong way around? 10 to the minus 8. So roughly this, with our system, we would be roughly somewhere here in between. You can see that molecules at probably about 120, 130 kilojoule per mole desorption energy would probably be the worst. And here we're roughly at a 1 year desorption time. So you can see one monolayer to desorb would take about a couple of years, a couple of months to a couple of years. Those very, very strongly depend on what molecule we have and what room temperature we have. You can even notice that if you look at the logs of our instrumentation, if we have a sunny day outside and the sun is shining directly on the chamber and it gets 1 or 2 degrees warmer, you can see that in the vacuum levels, just because the residual desorption will just speed up a little bit. And here we just have some typical desorption energies. This is what I could find in literature. Typically, you don't really find the ones that are most important for us, but you can see hydrogen from platinum. This is something that sticks pretty well. Hydrogen from ruthenium doesn't stick pretty well, but typical desorption energies can be around that sort of energy level. So what happens now if we go to elevated temperature? Here we've got 573 Kelvin, which would be a typical bakeout temperature. And there you can see that, that even for the pressures that we're looking at, the desorption times are more in the minutes rather than the hours or years. What that means is that you don't need to bake your system. I know people that build ultra vacuum systems that are confident enough that they don't need to do any maintenance, that they just close them up, leave them for a couple of months, and then they're at base pressure as well. But then you need to have the patience, and you don't have to need the instrument. But what we do is go to these temperatures, and then our desorption times are relatively short. Still, baking typically takes 24 to 48 hours. The reason for that is that very often we have thermally insulated parts in the system, and it just takes a little while until they warm up. If you just want to bake, if you just have a chamber and you want to bake the surface, as soon as everything's warm, everything will desorb in a couple of minutes, and then the contamination is gone. Okay, so standard vacuum chambers. Typically, we have stainless steel, 304 and 316. So for everyone that's not a steel person, it's essentially just regular austenitic stainless steel, the stuff your cutlery is made from. Nothing too fancy. It's because it's got good weldability, it's easy to polish, and has good corrosion resistance. Very often, if you want to polish electro-polish systems, so produce even better surface qualities, we go for 316L because it's better to electro-polish. And typically, we also use electroslag refined grades, and you can only get them in 316 anyway. I think that's even a bigger reason. But certainly, almost all components are available in 304, and some are available in 316 and 316L. This is the standard vacuum system stuff. You will get some outgassing from that. So here we've got outgassing of different materials over time. And you can see that if you look at different materials, if you've got something like neoprene, like a polymer, you get a lot of it. I have no idea what araldite is. But here you've got brass. Brass, very often we have the problem that the zinc or the tin in the brass or the bronze can be a problem during the baking. It's very often, that's why we don't use that one. But you can see stainless steel here starts out strong, but then eventually will go and taper off. And aluminium starts out worse and then eventually becomes very good. The reason for that is that aluminium the aluminium itself has a very low hydrogen diffusion rate, and as such we don't get hydrogen diffusing out of the chamber, but it also has a porous oxide, a slightly porous oxide. Aluminium oxides, a lot of dirt typically hides, a lot of sorbed material usually hides in that oxide. So initially you need to get rid of all the dirt that's in the oxide. Maybe you can, maybe you can't, but then it gets very good. And then with stainless steel, eventually the hydrogen is going to be the last residual to go. Of course, baking is a little bit more limited with aluminium compared to stainless steel, but it's a different story. What's missing here is titanium, and titanium is our friend. So we are building more and more systems here in Erlangen from titanium. And the reason for that is hydrogen permeability. So here we've got measurements of accumulation of hydrogen in metal in the vacuum pulp as a result of permeation from the atmosphere at 25 degrees. And you can see, okay, it will go very quickly with low carbon steel and relatively slow with copper, which is FCC. Here we've got BCC materials. If we look at the permeation constant versus temperature for hydrogen, you can see, okay, this is nickel, a low carbon steel. Do we have a stainless steel? No, but probably somewhere in the middle. You can see aluminium, very low penetration. And just to see that there's orders of magnitude in between. The reason why I put that slide on is because the general wisdom was, and to an extent is, that some of the hydrogen that goes into the chamber diffuses through the chamber into the vacuum. This is not something that we can really confirm because our experience, especially with ultra clean vacuum systems, is that this doesn't necessarily happen, and probably the contamination mostly comes from the dissolved hydrogen in the metals themselves. Okay, so which alternatives do we have? We can use aluminium chambers, or we can use titanium chambers. The good thing about aluminium chambers is that they have a very high thermal conductivity compared to stainless steel, so it's much quicker to bake the system because everything will just thermally equilibrate very quickly. And we have a 7 orders of magnitude less hydrogen permeability, which gives us a really good clean vacuum. But the problem is, and the reason why we don't usually use it all that much, is because baking temperatures are limited, because aluminium, it's precipitation hardened aluminium, 60, 61 very often, and so the baking temperature is limited. And what's even more important is aluminium is relatively soft, and if you have ever handled ultra vacuum systems, you'll know that if you If you hit a flange the wrong way, it will get a nick in it, and then the chamber is done. And this is really, really critical with aluminium CF components because it's very easy to ruin your chamber, and this is one of the reasons why we don't use them. As the alternative, we have titanium. And titanium has a relatively low thermal conductivity, so baking is somewhat slower. We don't get any hydrogen from the chamber. We also get no carbon. I don't know if that's really relevant, but that's people that try to sell that very often bring that in as well. It's lighter than steel, which may or may not be relevant. Sometimes the chambers still turn out heavier than the steel chambers, just because you need thicker wall thicknesses, because they're typically welded tubes, because you can't get them as finished tubes. You have to make the tubes yourself by welding, and then you need thick material in order for it not to warp. And yeah, very well suited for extreme high vacuum capabilities, but it's expensive. But I would cross it out. It's usually not a major expense. So our titanium chambers typically didn't contribute to the expense of building the system much at all. So I'd really put it in relatively expensive, but it's not the main contributor to the instrument costs. Okay, so this was the chamber material, but of course we also need other materials. And the materials we typically need is materials that either thermally insulate or thermally conduct, or electrically insulate or electrically conduct, because this is the typical requirements that you have, and combinations thereof. Sometimes you need an electrical insulator that's a thermal conductor. Sometimes you need a thermal insulator that's an electrical conductor, and so on. Okay. And for that, we can use ceramics, and we also need to be able to make the parts for our system from that. And typically, what we can use is machinable ceramics. Machinable ceramics are ceramics like Maycore. Maycore is, I think, alumina beryllia, some combination of that. So it's essentially, it's a ceramic that you can machine, so that you can mill, turn, and so on. The problem with that is just that Maycore becomes conductive after long irradiation, which is not important for us. But if you ever build UHV systems for example, synchrotron and so on, where you really irradiate stuff for a long time, then this can become a problem. So the thing about ceramics, though, is almost all of them almost all of them are pretty okay to use, but usually we use the ones that we can match in thermal expansion coefficient to the metals that we use. Because while you bake, your system obviously gets warm and cold and expands and contracts. So you need to have things that are thermally compatible with each other. And finally, if we want to have electrical insulation and thermal insulation, we also can't get around polymers really. If you need both of that. And polymers you can use in ultra-high vacuum, but it needs to be polymers that have a very low outgassing rate. And there's a couple of those. And essentially, they are either polyimide-based, PI-based, or PEK-based, or some perfluorinated polymers, like PTFE, PFE, or Viton, which is perfluorinated rubber. And they are also fine to use, but they tend to have temperature limitations. So typically, typically we use Viton, which is a fluorocarbon rubber, as seals where we can. We use Teflon, we use PTFE, PTFE also in areas where typically we need something with low friction. But the problem with PTFE is that it's easily hardened and breaks down under irradiation, and it also tends to emit small amounts of fluorine. A good example of that is there are ultra-high vacuum transmission electron microscopes that use PTFE a lot inside, and they always seem to have a fluorine peak in their microanalysis data, just because you get some outgassing. What we use a lot is either polyether ketone or polyimide. Polyimide you might know as Kapton. This is typically these sort of yellowish, brownish, yellowish films. And they are both suitable. PEK is good for mobility and machinability, and it's very widely used in UHV components. And it's a relatively expensive polymer, but for the amounts that we need, it's not super expensive. Polyimide is also very well suitable, but polyimide is extremely expensive. So we've got little rods of polyimide downstairs about this size. They cost about €1,000 each, just the material. So if you see dark brown polymers lying around in the lab, put them where they're locked away, because we don't want to lose them. Okay, and I think we'll jump over that. That's just the data. So lastly, for us, 3D printing is something that we also like. The question is, can I use 3D printed parts? Well, probably not from acrylic. So if you use our printers downstairs, like our resin printers, probably not, because you can see the amount of residual gases that you get is into the 10 to the minus 7, 10 to the minus 6, 10 to the minus 7 millibar range. But if you use, and if you have, even if you have 3D printed nylon, which you can also get similar levels of vacuum. But if you have metallic 3D prints, here the example is silver, then you have relatively little issue. And the residual is the residual that you always have, which is hydrogen, which comes from the chamber. We haven't yet used a lot of 3D printed parts in our systems, but that might change. Okay, so the question is then, how do I build a system from that? And typically we build systems using so-called con-flat flanges. And this stands for con-flat flanges. And what they are is essentially you've got very sharp edges. We've got a flange with very sharp edges that are pushed into some kind of soft metal seal. And con-flat flanges are just one version of it. If you ever get to take apart one of our ultra-high vacuum valves, they have a different shape. Still same principle, but a little bit of a different shape. And typically the soft metal is copper that we use. Soft metal that we use is copper, but you can also get them in indium, for example, and you can imagine all kinds of soft metals that you can use for that. So typically for larger systems, you can get indium wires, for example, for sealing. And the sealing action is a metal seal. It's a metal-to-metal seal. And the reason for the metal-to-metal seal is because we can get it to high temperatures, typically up to 450 degrees C. So the flanges themselves, it doesn't mean that everything else in the chamber will be able to go to the temperature, but the flanges themselves can go to 450 degrees C. And they have a limited number of standardized sizes. And they are, if you work with these systems a lot, you will know them on top of your head pretty quickly, which is 16, 40, 63, 100, 160, 200. And then the larger series start. But this is sort of the most common ones, and you'll see them around a lot. And typically, you kind of have to design your system around these sizes, and they actually stand for the clear bore diameter. So this is, since I've worked with a lot of them, I know this is a CF40, and this means that internally we have a diameter of larger than 40 millimeters, at least 40 millimeters. And you can already see, okay, there's a big jump between 16 and 40, then a smaller one between 40 and 63, and then about an equal one between 63 and 100. But this is essentially, you will get all of the components only in these sizes. Sometimes you will have to deviate from that. So currently we're building a system for an ultra vacuum system for neutron scattering. That is Olli is building that system where we need a rectangular window, and then you have to design it yourself essentially, and then everything becomes custom-made. Everything takes much longer to make, much longer to order, and you get no guarantee that it works. With these, you can just buy them, and a small flange will cost very little money. even though most of the ultra-high vacuum systems do cost a lot of money. When you design a system, you have to consider two more things. And the first thing, this is just an escape from one part out of a vacuum system, is that usually you will need some screws somewhere to attach stuff to other things. And then you always need to make sure that there's no dead volumes. So just imagine you screw a screw into here, and then the volume behind the screw would be trapped. And the air would just slowly come out over time. And you will have something called a virtual leak. So you'll try to find a leak if a flange is leaking and you don't find a leaking flange, and eventually it turns out you had air trapped somewhere in a hole. Because always remember, we're working at 10 to the minus 10 millibar, let's say 10 to the minus 9, and it's easier to calculate, which is 12 orders of magnitude removed from ambient pressure. So if you have a volume of, let's say, 1 cubic centimeter, then it's 10 to the 9 cubic centimeters at this pressure. So very large volume. So always bear that in mind that small trapped volumes at these low pressures suddenly become very large volumes. So typically what you can do is drill escape holes or cut an escape slot, things like that. The other thing is something I already talked about, which is thermal expansion. Very important if you, for example, have a window which is some kind of glass, or now that we're building deep UV laser systems, it needs to be sapphire or maybe diamond. And this will have a different exponent of thermal expansion than the flange itself, and you need to somehow combine them. Typically what's done is that you have some kind of sheet metal piece that sort of can take some of the expansion, but of course it's always good if you can match the thermal expansion. Typically those windows we have alloys called KOVA. KOVA is called KOVA because it's got the same thermal expansion as glass, for example, as flint glass. You always need to find, if you really mount things on top of each other, you need to make sure that they have sort of similar thermal expansion coefficients. Okay, the question is now, we have a chamber. How do we get that chamber to ultra-high vacuum? How do we get the chamber to ultra-high vacuum? And this is, of course, by having a pumping system. And a pumping system for an ultra-high vacuum system typically consists of 3 pieces, or 4 pieces really, which is the work chamber, which is the chamber where we do our experiments. Then we have some kind of ultra-high vacuum pump. And again, the ultra-high vacuum pump typically has no gas escape route. It will be some kind of sorption pump. This is kind of not 100% the case anymore, as turbopumps, which we'll look into, are now getting into regimes where you can get to ultra-high vacuum with a turbopump, which removes gas, but typically that's not the case. And so what we need on top of that is some kind of roughing pump that gets us from ambient, from around 1 bar down to wherever the ultra-high vacuum pump can start. Maybe 10 to the 0, 10 to the minus 1, 10 to the minus 2 millibars, depending on what it is. And we need some kind of vacuum gauge. Sometimes the pumps connect as gauges, or the gauges connect as pumps, but typically we need both. And we'll see later why that is the case, why they can act as gauges or act as pumps. And so we'll look into roughing pumps, turbomolecular pumps, and ion getter pumps, or getter pumps in general, not necessarily ion getter pumps, sorption pumps. So roughing pumps, for us there's four important types, and we can group them in 2 different groups, which is dry pumps and oil lubricated pumps. The simplest dry pump is a membrane pump. It's very simple. It's essentially a membrane here. It's also called a diaphragm pump. And the membrane is moved by an eccentric motion up and down, and then just has a suction and an exhaust port with valves to avoid backflow. You can see very simple pump. all you have to, it's clean, and all you have to do is every once in a while change the membrane, because the membrane is sort of a rubber membrane, and probably after 1 or 2 or 3 years, typically those membranes fail, then you have to replace it. But it's a relatively simple operation. They're dry, they're relatively silent, and they don't cost a lot of money, and they get you down to typically 1 to 2 millibars. And modern turbopumps can actually deal with quite a good amount of back pressure, so they're typically these days good enough to back turbopumps, and we use those a lot, for example in the LEAP system, but also in other ultra vacuum systems that we operate. The other one that's very popular are rotary vane pumps. Rotary vane pumps, Drehschieberpumpe in Deutsch. Rotary vane pumps are pumps where you have a sort of eccentric motion as well, where you have 2 slots here, so two baffles here that move in and out, and through that, through the rotary motion, you get a compression motion of the gas that you suction in. And they are good. They are oil lubricated, which means they can deal with contamination pretty well, which in ultra high vacuum systems is not relevant because you're not typically pumping out dirt from your chamber. They are relatively affordable. You can get them on eBay or on AliExpress for like $150. Of course, not the professional ones that we buy, they're a little bit more expensive, but you can buy them for very little money. And they will get you down to about 10 to the minus 3 millibars. And the limitation thereby is the outgassing from the oil. And this means we don't want to get the oil anywhere but the pump, and this is why we usually try to avoid them. Because if something goes wrong, say you've got for example, a electricity outage, what can happen is that you can get some backstreaming of the oil into your system. And if you get a pump oil into an ultra-high vacuum system, it's going to be very, very difficult to remove it again. But we still use them with some precautions, typically with some buffer tank in between so that the oil can stream back. And then they just chuck away for a long time, very low maintenance, and very good and relatively good vacuum. Scroll pumps are also a type of pump that we use very often. And essentially, there are 2 scrolls that move in a fashion like this with respect to each other. So one is static, and the other one moves in an eccentric motion. And through that, we have a trapped volume. And that trapped volume moves from the outside to the inside, or the inside to the outside, depending on on how the thing is set up. This is what facilitates the pumping motion. Typically, those scroll tips are made from PTFE. So they're sort of self-lubricating, this makes them, you can also get them lubricated, but typically they're dry, and they can get you down to about 5 times 10 to the minus 3 millibars. They have one downside though, and that is that the scrolls, they rub on each other, and if you don't have any gas flow continuously going through, then you have the problem that any wear material gets accumulated, and that accelerates the wear because then you have dust inside, and then they can wear relatively quickly. So they're great for things like load locks and so on, where you pump down pretty regularly because then all the dust gets cleaned out, and then it's good to use again. But very popular, they're in a lot of our vacuum systems. Also the regular vacuum systems, for example, all of our SEMs have scroll pumps as pre-pumps as well. And then finally we have Roots pumps. Roots pumps are essentially pumps with Drehkolbenpumpen in German. So they're pumps where you have these 2 pistons, rotary pistons, that with very tight tolerance move with respect to each other. And they essentially seal against the outside through very, very narrow tolerances and produce a pumping action through that. And typically, they don't just have one stage, but multiple stages. And the good thing about them is they're dry, they're very clean, and they can get you to a very good vacuum, and they're very expensive. And one thing is they're very, very loud. So in the beginning, we had a couple of them running, but by popular demand of all the PhD students, we don't run any roots pumps anymore because you literally need to sit in the room with hearing protection on. This is why we typically don't use them. But we have some of them still kicking around. Okay, so typical membrane pump. So this would be the one that's used in our commercial atom probe. It's a Pfeiffer, MVT, bar, whatever. And what it is a dual stage diaphragm pump. So there's 2 diaphragm stages. And that brings us down to a bottom out pressure of about 1 millibar. That's very typical for these pumps. But you can go and look the bottom out pressure up for the individual pumps that you want to use, but this is typically what you can expect. But for modern turbo pumps, that's usually pretty okay. Which brings us to turbo pumps. So turbomolecular pumps are pumps that we use in a lot of systems here at the Institute. Not just ultra vacuum systems, but also high vacuum systems, like for example, our vacuum furnaces use turbo pumps, our electron microscopes use turbo pumps, and so on. So very popular pumps. And essentially what they are is they are sorption and desorption kinetic pumps. So this is the simplest form, invented about over 100 years ago. And essentially what you have is a spinning cylinder that spins very fast. And what you get is you get a molecule coming in from this side, adsorbing on the cylinder, and then eventually desorbing again. And if the cylinder spins fast enough, then you will have a net motion of molecules on the secondary side. You can already imagine why they're called turbomolecular pumps, because it's a molecular sorption-desorption process. And this means that they need to spin very, very, very fast. But because it's a sorption and desorption process, there's always a probability for desorption into the inlet. And the result of that is that these are only differential pressure pumps. So the out pressure, essentially you will have a pressure ratio, of intake to output pressure. So a pressure ratio between inlet and outlet pressure that is essentially exponent of some geometry factor times the blade velocity. And so you can imagine the faster the blades spin, the better the ratio is. The faster the blades spin, the better the ratio is. Of course, this is not what modern pumps look like. Modern pumps look like turbines, but don't confuse them with an actual turbine, because an actual turbine is a gas flow device, so you will have some gas flow that you're directing. In this case, you're literally just giving the molecules a sort of an average speed that points more towards the outlet than the inlet. And typically we have a rotor and a stator, and so if we look from the perspective of a molecule from the incident side effectively sees at the velocity, sees an area or an angular area of this size for the adsorption, whereas it sees an angular, so if the blade's spinning, it sees a larger angular size when it's desorbing, because when it's desorbing, it has the same speed as the blade. When it's adsorbing, it has a speed relative to the overall world frame. And this is just the principle. So always remember, it's a differential pump, and the blade speed of the blade essentially gives us the pumping speed. So this is a current model. This is a Pfeiffer high pace, and I've just picked that one because we use a lot of them. And not all of them, all of the pumps that we use are Pfeiffer ones. There's also some that we use from Edwards and some from Leska and God knows what companies. But they all work in relatively similar ways. And the most important thing for us is that we have to have some kind of bearing that supports the fast spinning of the blades. And typically, a 80 liter per second turbo pump, which is a turbo pump that fits on a CF63 flange. Yes, it will always find some very distinct sizes with the pumps as well, because they're typically matched to the flange sizes. This would be one for a, in this case, we haven't talked about KF flanges, so this is an ISO K63 flange. It's essentially a rubber-sealed version of the CF63 flange, of the conflat flange. Typically, they have the same sizes, but you can get them in either rubber-sealed or metal-sealed, and this is the rubber-sealed version. And then it has about 80 liters per second of 80 liters per second of pumping speed. And what we typically have is we have one permanent magnetic bearing and one ceramic bearing. So these rotors are typically half suspended. Half suspended because a pump like this runs at 1500 hertz. 1500 hertz or 90,000 RPM. But this is obviously pretty fast. So you need a bearing to match that fast motion. So this brings us to the biggest downside of turbo pumps, and that is that they are vibration sensitive. So a turbo pump, if you have a turbo pump on a device that sits on a table, if I do this, what will happen is you will hear very bad noises from the turbo pump, and if you're unlucky, the turbo pump might even blow up. Just because the rotor will start touching the stator, and then will just be slowed down very quickly. And there is one example of an atom probe at colleagues in France, where someone has put where it was an air suspended table, and because it was a laser atom probe, and someone has put something too hard on the table, and exactly that happened. The turbo pump blew up and took essentially everything in the chamber with it. So be careful with turbo pump systems. Don't move it around when the turbo pump's running, because we have some systems where you can do that, could do that. For example, Olli Nagel's new system is currently on wheels, and the turbo pump's running. So if you go there and you shake it, that would be very bad. So don't do that. And so here the maintenance is bottom bearing typically needs to be changed every couple of years. But apart from that, they're pretty low maintenance. And they're very clean and very easy to operate. And they can, together with a backing pump, get you from ambient pressure down to, where is the bottom out pressure? Bottom out pressure, bottom out pressure. Bottom out pressure. Doesn't say it anywhere, but it should be, bottom out pressure. So you can see we're at less than 5 times 10 to the minus 10 millibar. So higher ultra high vacuum level, but still ultra high vacuum level. What you can also see is that it will have different compression ratios for different elements. So heavier elements are easier pumped than lighter elements. So it's harder to get rid of hydrogen, for example, compared to argon or nitrogen or something like that. Very important to remember. Remember, it's a differential pump. So what we do, for example, in one of our systems is back a turbo pump with another turbo pump. Then you can go to even lower pressures than that. Yeah, and this is what happens if you have a turbo pump failure. And if you want to see a failed turbo pump, you can go into Heinz Werner's office. He has one from back in the day when our old SEM had some issues with gas coming in too early when you vented it, and eventually the turbo pump blew up as well. And not as violent, so it didn't take the entire SEM into its grave with it, but you can see if something looks like this, and it broke at 1,500 hertz, 90,000 RPM. You can imagine parts flying around in the chamber being a problem. Okay, so this was mechanical pumps. The other thing that we very often have are sublimation getter pumps. In this case, the principle is chemisorption. So you have some chemically active surface, some reactive surface, and then you have a desorption time that's dependent on the desorption energy, and then obviously the temperature. But you can have sorption energies that are so high that essentially you've trapped the gas atoms or the contaminant atoms. And typical sorption energy of oxygen on metal surfaces, because oxygen is obviously something that we pretty regularly would like to pump, is in the range of 12 to 70 kilojoules per mole. So relatively low if you compare to what I've showed you from the bakeout stuff, as this is something where the oxygen would sort of float around in the chamber and not stay adsorbed on the surfaces. But if you have oxygen on blank titanium, so titanium without an oxide on top of it, we're more talking about 1,000 kilojoules per mole. Which means if the oxygen bonds to the titanium, it will never ever leave. It will just stay there. And this is the principle of chemisorped of getter pumps, that we're using that chemisorption. Of course, if you have something that's not chemically reactive, like an inert gas atom, these pumps will do absolutely nothing. So if you have something like helium or argon, then these pumps will do absolutely nothing. And if you have an air leak, for example, always remember air is about 1% argon. So if you have an air leak, you might get rid of the nitrogen, you might get rid of the oxygen, but you will not get rid of the argon through these pumps. Okay, yeah, the time's probably not that important. Typical sorption pumps that we have are either titanium sublimation pumps. What we do here is we have a titanium filament, and we just have titanium sublimating from some hot titanium wire, and then resubliming onto some cold surface. A cold surface can be room temperature, or can be liquid nitrogen cooled, or can be water cooled, depending on whether you just want to intermittently do that or continuously operate it. For us, typically, when we work in ultra-high vacuum, we do a run of titanium sublimation, and then that's good for a couple of days or a couple of weeks. But if you're in semiconductor processing equipment, you might have them running constantly, and then you need some water cooling in order for continuous sublimation to happen. But these are very practical, very easy to run pumps. We have one of them on our field ion microscope that we used in there because we wanted to do atom probe tomography for field ion microscopy. It wasn't all that important. But this obviously means you're sublimating some titanium and you're inputting heat into your system, which you may or may not want. So an alternative are so-called non-evaporative getter pumps. So this is titanium sublimation pump and non-evaporative getter pump. And what a non-evaporative getter pump is the same thought. You produce a highly reactive surface of typically some titanium or titanium zirconium or zirconium aluminum alloy. There's a couple of different ones out there. And that then sorbs just as the titanium would sorb here. But in this case, it's an alloy where the oxide that swallows its own oxide at a reasonably low temperature. Titanium does it as well, by the way, but by titanium, you need to go up between 450 and 600 degrees C before titanium takes up its own oxide, which is not really doable for a ultra vacuum system to really go to these temperatures. With NEG pumps, it's typically more like 250 to 450 degrees. So you just heat that up, typically buy them with heating integrated, and then this thing will just go and sorb. The good thing about them is that they're relatively easy to operate. They don't need any power while they're running. Once activated, they will just keep sorbing for a very long time unless you have a leak or something. But if you put in too much contamination, they will eventually turn into all oxide, which means dust. And I've taken apart an old atom probe that had a non-evaporative getter pump that by the end was essentially just dust. We took it apart, and I first thought, okay, we can still use that one, but then when you touch the pellets, the NEG pellets, it was just crumbling to dust. and they're relatively expensive. But we have quite a few of them in operation in our atom probes and also in our titanium thermal in our thermal desorption system. So very good because it's they're very robust pumps. Unless you give them too much contamination, then they become a bit of a problem. Another pump that we use, and we use that one a lot, is a so-called ion pump, ion getter pump, IGP, ion getter pump. And that's the main pump, for example, in the LEAP system. But that's also the main pump typically in transmission electron microscopes, including our transmission electron microscope. It's also the main pump in electron microscope columns. So all our field emission electron microscopes also have ion getter pumps as pumps. And the way that they work is essentially that you have an anode and that they have anodes and cathodes in two directions, and that you produce a magnetic field that ionizes any gas atom that comes in, and then the gas atoms get accelerated towards the cathode, and thereby to do things. First of all, they might get buried, but also they can sputter the surface of the cathode, which is typically titanium, and by that action they produce fresh titanium surface. And then you have chemisorption again. But because the ions also can get buried, you also have some pumping action for noble gas atoms. Because essentially just shoot the noble gas atom into the material and it just gets stuck there. It's not great for noble gases, but it has some pumping action for noble gases. Basic principle. So we have an anode cylinder and a cathode plate in this case. It's a very typical way of doing that. And through a large magnetic field, you will have any ion that's produced in there flying around in a corkscrew fashion, which just increases the residence time for it to get ionized by some collisions, and then eventually it will hit the surface. Downsides are big magnets. Big magnets mean very heavy pumps. They're big and heavy, but they're very robust to operate. For us in atom probe tomography, they also have one additional downside, and that is some of the ions typically can escape and can get sucked into our detector. So we need to have some good shielding in order for the ions not to get sucked into our detector. This is, by the way, the pump that we have in the LEAP system. And one thing you can see is that it weighs about 100 kilos, a very heavy pump. Which means if you design the system, the only place you can put the pump is essentially at the bottom, just because it's very heavy. You can't put it on the side, top, or anything. Okay, so noble gas pumping, typically you can see here, helium pumping, if you have got a regular one, is about 10% of the pumping speed compared to something like a nitrogen or water vapor, but there's some versions where you get improved pumping speeds for noble gases, if that's something that you need. But it can also help for instruments like a field ion microscope, because in the field ion microscope you typically want to pump everything but the noble gas, because that's what you use for imaging. So there, this is even helpful. Okay, which brings us to the cryocoolers. So the cryocoolers that we use are typically Gifford-McMahon cryocoolers. So there's essentially 3 different types of cryocoolers, and we probably won't go through all of the different ones, but I think you all know what a Stirling process looks like. So a Stirling process essentially means that you have some kind of displacer and regenerator, and you have heat going in here, and through compression of, in our case, helium, because the temperatures we're at, only helium and hydrogen are even anything but solid. Everything else is already solid. So we're using helium. Great. So we're using helium, and the helium gets cooled on the primary side. On the secondary side, the heat is taken out. The problem with Stirling machines is that they're relatively expensive to build, because they're custom piston systems. So we are typically using Gifford-McMahon systems where the compression bit, so here's the compressors, the compression bit and the displacer bit are separated. So you can use just a regular type compressor, regular gas compressor to compress the helium, and then just have a cold head that does the displacing motion. And this is typically the sound that you hear when you go into an atom probe lab, is the sound of the displacer going back and forth. So these are all closed cycle helium refrigerators. You can also have open cycle refrigeration, essentially just use liquid helium. But this is typically only economically feasible if you have some helium recuperation, which we do not have in this building. But for example, the people over at physics, they have that in their buildings. So they can just go and get some liquid helium from the helium liquefier, which the university owns one, a relatively big one actually. So we can make our own liquid helium, and then you can cool, which means you don't have this awful sound and you don't have the vibrations that are caused by this. Good, and I think we're going to go relatively quickly through the cryos to just quickly go through the pressure gauges. So we also need pressure measurements, and this is something that's going to be very important for you if you operate any vacuum equipment here, be it an atom probe or an SEM or something else, to understand what the measurement readings are. And essentially, we have hot cathodes. So we've got hot filament and cold cathode gauges. Essentially, at UHV, we typically have ionization gauges. So it's not a mechanical gauge like a Bourdon gauge that you know, Bourdon manometer, that you know from, I don't know, your regular vacuum equipment that, where you just have the dial, or for example, the high pressure equipment. So our 1000 bar systems, for example, they use mechanical gauges. But here we've got ion gauges. So essentially, we ionize the residual contaminants and measure the current that they produce. And typically, we can do that in two ways, either by having a hot filament, where we have ionization at a hot surface, or by having a cold cathode, which is essentially exactly what I just explained with an ion getter pump, but just used as a gauge. That's why I said ion getter pumps you can use as gauges, or cold cathode gauges you can use as ion getter pumps. This is where ion getter pumps even come from. Back in the 50s, 60s, when they were developed, people have noticed that gauges with the chambers with these ion gauges tend to get, the vacuum reading tends to get better over time. At first they thought it's some kind of drift effect, but eventually it was clear that no, actually the vacuum gets better because the gauge itself acts as a pump. And the hot filament gauges, the good thing about them is they're very simple. They have no magnetic fields, and I think next time at the next lecture I'll just bring some of them. I have some old ones lying around. But the downside is they produce heat and they have a finite life. And typically we work at 20 Kelvin, so we try to avoid any heat sources. The good thing about cold cathode gauges is they give off no heat. But the magnetic field may interfere with your measurement if you have something where magnetism plays a role. And the reading, again, depends on the gas type. And this is very important always to remember, that the gauge reading doesn't mean you know what the vacuum is, because you don't know what the partial pressures are. You don't know if the vacuum is exclusively hydrogen or nitrogen or argon or something. Okay, and for us, very important, just like the ion getter pumps, also we get ion emission. So some of the ions that get ionized make their way out of the gauge and can get sucked into the detector as well, which just means we need to be strategic where to place the gauge. So typically, of course, you get a lot less emitted from them compared to an ion getter pumps. Okay, we're not going to go through the details of how they work. Here just, if you actually want to know with a cold cathode gauge what the pressure is, and then there are conversion factors. Typically, the reading is for air. So if the residual gas that you have is exclusively air, maybe you have a leak, then the reading is correct. But if it's hydrogen, for example, we have a strong underestimation of the pressure. If it's all something like argon, then we have an overestimation of the pressure. So unless you know what the partial pressures are, always bear in mind that you don't know exactly what the pressure is. Of course, now with the thermal desorption system, we have one where we actually get partial pressure measurement, but this is a whole different topic that we're not going to cover here. At higher pressures, I said these ion gauges, they only work at very low pressures, so typically below 10 to the minus 3 millibars. So we also need some measurement of pressure between 10 to the minus 3 and ambient pressure. And that's typically so-called Pirani gauges. You also very often see them as PIG. And they're very simple devices. It's just a hot wire. And what we measure is the change in conductivity of that wire that stems from cooling by convection. So the gas molecules essentially cool the wire, and we measure the change in resistivity. Again, we have some dependency on gas type, but it's relatively gas agnostic, and it can take us roughly from 10 to the minus 3 to ambient pressure. If it's a regular one, there are versions with pulses, where you essentially let a lot of gas absorb, and then you send a pulse, you just heat it up for a very short amount of time. Then we can get down to 10 to the minus 4. And these days, there are also some on MEMS bases that can go down to 10 to the minus 5. We'll find all of them in some systems that we have. Just bear in mind that that's how the measurement works in this case. And this is just an overview of where we can use them. So our ionization gauges typically go down to 10 to the minus 11. On the Oxcart, for example, the vacuum is better than what we can measure with regularly available measurement gauges. But there you can get some custom-made ones, very special hot ionization gauges and so on. But for us, if we know from the experiment we see no residual contaminant in the experiment, then I don't know if we really care if we can precisely measure what the pressure is. And then we have our Pirani gauges at higher pressures. And typically what we have is so-called wide range gauges, which are a combination of the Pirani gauges and either a hot cathode or a cold cathode gauge. So the Pirani gauge essentially measures from ambient pressure down to some set point, typically 10 to the minus 3, and then the gauge switches over to either cold or hot ionization. And so if you pump down your system and you see suddenly a jump in pressure, it's typically the switch point of the wide range gauge to go from Pirani to ionization gauge. Okay, which brings us to the last important bit for the atom probe, which is the detector. And the detector in all current atom probes a microchannel plate as preamplifier plus a delay line for position encoding, plus some intermediate electronics. And this is a model of a cross delay line single ion detector. And we can go downstairs and I'll show you what a real delay line detector looks like, because we are one of the very few people that just have one lying around that's not used somewhere. And so essentially these things is first the microchannel plate is a preamplifier. It's a pit here in front and it's a glass plate. We talked about it last time already. And here at the back is a delay line, which essentially is just wound wires that are used for the position encoding. And eventually those wound wires go into some electronics we'll have a look into. First, typically in the so-called constant fraction discriminator, and then a time to digital converter. But these days we could also use analog electronics, analog to digital converters. They are becoming fast enough for usage in atom probe. And there is one instrument in France that already runs on this schedule. Okay, so first, how do we amplify the atoms? And this is done by microchannel plates. And what microchannel plates are is just a lot of scintillators. So scintillators is an electron multiplier. So you have some incident electron that hits a surface somewhere, produces secondary electrons, and they produce more secondary electrons, and so on and so forth. So essentially, you get an electron avalanche. So here it's drawn with an electron, but you can also use an ion or a photon to do that. They just need to have sufficient energy, or sufficient impulse. What microchannels react to is impulse. So mass times velocity, which means that heavier ions typically can be a problem, but not within anything that we are concerned about. So for all of the ions we are concerned about, they work perfectly fine. There's a couple of manufacturers out there in atom probe. Very often you find ones from Hamamatsu, and I'll show you later on why. But you can buy them from a couple of different vendors. And what they do is essentially typically give you a gain of around, so the gain, the amplification, is typically around 10 to the power of 3. So about 1,000 times. And what we typically do, therefore, is having a so-called two-stage MCP setup. So we have two on top of each other, so that we get a gain of about 10 to the power of 6. And the way we do that is, of course, we need to have some kind of supply voltage, high voltage, that triggers that electron avalanche. And here we can see the gain depending on the supply voltage. Typically, we operate at about 1.2 kilovolts per plate, so around 2-ish kilovolts, so 2 to 2.5 kilovolts for the entire stack. Main application of those, by the way, is military-grade night vision. So this is why in times of crisis, sometimes these things get characterized as dual-use goods, and it gets a little bit more difficult to buy them, or you have to fill out stuff and saying, yeah, I'm not going to ship them to North Korea or something, because that's where the main application is. Okay, so typical setup, chevron stack because we have an atom probe specimen and we've got an ion emitted. And chevron stack means that the channels are at an angle, and the angles are twisted 180 degrees between the subsequent plates. The reason for that is that if we have an ion and it flies into a channel and it has the exact orientation of the channel, it will still hit a channel in the second plate. So it still has a high chance of hitting a channel in the second plate. And two again, because we have a 10 to this, we want to have a high amplification. We use 2 and not 3, just simply because eventually we'll get into saturation and we'll not be able to extract more charge out of a single ion hit. And this is already the case if you have ions hitting after two plates. So you can use 3, but it's not going to help you anything. So this is a typical setup. So for positive ion detection, so you have the stack of the two things here, and then in this case you have a phosphor screen for imaging, and this is what we do for field ion microscopy. Just the electron cloud that we produce goes into a phosphor screen. For atom probe, of course, we want to have time and single particle time and spatial resolution. There we need to have some way to read out when this electron cloud was produced and where it was produced. So how do we make them and what are the limitations? Well, there is a very distinct process to making them. And this is also one of the reasons why we have some residual measurement background, because we need to have some glasses where we have one channel glass and one soluble glass. Where we can make out of the channel glass, we can make a tube, put a soluble core, so a soluble glass inside, so that we can get some kind of inner and outer tube. Stack them together, then they're fused, drawn out, stacked further, and eventually out of an entire bundle, we cut a disc. And this is our microchannel plate. And in order to be able to do that, we need to have a glass that's soluble inside a glass that, that's not soluble in some kind of solvent. The only glass combinations that we have are using potassium-containing glasses for the channel glass. And potassium has some residual radioactivity from potassium-40. And this is the reason why we have some background in our detection always. Because the potassium-40 will decay, and each decay, I think it's an alpha decay, I should look that up, but I think it's an alpha decay, and each decay event will trigger the detector. This is typically the background that we see. And after etching, this is what an MCP looks like, and you can already imagine if an ion hits here, nothing will happen, but if an ion hits in the channel, then it will get amplified. What that also means is that we have a detection efficiency, which is typically 0.6 to 0.9, depending on the type of the microchannel plate. 0.6 to 0.9, roughly. This is what the microchannel plate looks like. And what you can see is also that we have some bundle boundaries here. And you will also see them show up in your atom probe data because also the detection efficiency varies a little bit at those bundle boundaries. So they can show up in the atom probe data if you look with very, very good statistics. I talked about efficiency. So a standard microchannel plate has an open area ratio of about 60%. So ion hits between the channels, nothing happens. Ion hits in the channel, it gets amplified. So people a couple of years ago from Hamamatsu developed so-called funnel MCPs, where they used some ion processing to sharpen up the end bits. And so in this case, we're talking about an open area ratio of 90% active area. These 90% are just based on measurements like this one. So they put an ion current and just look at how much higher it is compared to a regular MCP. The open area ratio directly doesn't really have any meaning on an MCP like this, because theoretically, the open area ratio is 100%. But we don't see 100% amplification because some ions still get stuck somewhere here, or at least don't get amplified. Important thing to remember in this case is here, ions either hit the hole or don't hit the hole. Here, if they're somewhere up here, they may or may not get amplified. But of course, the higher the energy is that they impact with, the higher the probability for amplification. So here for these, we have a saturation at about 2 keV for the ions. So at above 2 keV, we amplify all the ions. Whereas for the funnel MCPs, we have a first plateau, and then it takes a little bit until at about 5 keV, all ions get fully amplified, or at least 90% of them get amplified. So we have some energy dependence. So how does the position encoding work? Well, it's relatively simple. I think we talked about it already last time a little bit. So we have essentially wire meanders. And the electron cloud that the MCP produces hits somewhere here. And it's relatively large. It might be a centimeter across, depending on how far away from. Okay, I think we're going to stop on time today. I hope next time there isn't going to be as much construction going on anymore. And what will happen is that this electron cloud then will induce a pulse that, just like if you throw a stone into a pond of water, you will have an electron wave moving towards the ends. And so if it hits somewhere in the middle, then you will get signals at about the same time on each side. If it hits somewhere towards this side, of course, you will get a signal quicker at, in this case, x1 than x2. And so essentially, we can encode the position by looking at the time difference. We don't even need a start time. But if we additionally have an external time reference, we can also say from the time average, we can also say when the atom hit. And so this way we get time. So we get x, y, and time. So we get x, y, and time from the time sum and a time difference. Of course, since a wire coil, it only works for one direction. It only works for one direction, so we need to have at least 2 coils to get x and y. Some detectors, you only have 1 coil because you might only be interested in one coordinate. For example, if we do some spectrometry, sometimes people only need one. Typically in atom probe, very often what we have is also a third one, and that's what you're going to see downstairs. So we have 3, so that you have one redundant delay line, which is great if we have multiple ions impacting and we need to figure out where the multiple ions hit. So state of the art is you can do single and multi-particle detection. We typically have spatial resolutions in the range of 20 microns, which depends obviously on how far the holes and the MCPs are apart. And temporal resolution is typically better than 100 or 200 picoseconds, but it's sort of in that range, say 100 to 200 picoseconds. We typically have detectors up to 150 millimeter active diameter. They're typically not used in atom probe for the reason that for these very large detectors, the MCPs typically have to have smaller holes compared to the parts in between, because it's a large glass plate and you need to be able to manipulate it without breaking it. And so typically we only use up to 80 millimeters because that's the largest way to get the funnel type MCPs. I know the colleagues in Stuttgart, for example, use detectors up to 120 millimeters. We can certainly go up. And nowadays there's some MCP manufacturers that can make capillary MCPs, the typical new type, up to 20 centimeters. Yes, you can make larger and larger detectors. And for improved multi-hit detection, we have these redundant delay lines. The patent was filed in the early 2000s, so they were already out 2 years ago. So now you can even buy them commercially without having to buy an entire atom probe. And the reason for the redundant delay line is essentially that we have a dead area. So remember, we have this pulse of electrons. And just imagine you have two electrons hitting close to each other. And this is just double hit distance, so you can see if one hits here and the other one relative to it hits here, then it's fine. But if it hits here and here, then this coordinate we can't recover. And just simply because we will have 2 electron clouds that are close to each other, we can't really distinguish them. We can't really distinguish them. And if you have a redundant delay line, we have additional information. And then you would only have a very small so-called dead area where you can't distinguish between the individual hits. And this dead area then typically is around 3 to 5 millimeters on the detector. The reason being that the electron cloud typically moves, or the electron wave typically moves with about 1 millimeter per nanosecond. And the pulse width is in the range of 2, 3, 4 nanoseconds. Let's say 4 to 5 nanoseconds. And so typically, if it's a distance closer than that, then we can't really distinguish it. Of course, this is because of the electronics in between, which we don't have time to get into. But if we have some smart electronics that can take those 2 pulses and deconvolve them, then you might be able to get rid of that just by that. Or might, we know by now you can. Our friends in France have done that. Okay, and with that, I think we're gonna just maybe quickly touch what a reflectron is, because one of our instruments has one. So before the detector, sometimes we have something called a reflectron. What a reflectron is an electrostatic mirror. And what it does is essentially, if the ions fly into it, if an ion has more energy than another one, then it flies deeper into the reflectron and has a longer flight path. And if you do that in a smart way, then you can compensate for energy differences in your ions. And the energy differences come essentially from the fact that if you use a voltage pulse, then some ions might come off at the beginning of the voltage pulse and some a little bit later. And so they might have a little bit of an energy difference. If you use laser pulsing, then they typically have no energy difference because the thermal energy you input is very, very, very small compared to the electrostatic energy you put into the ion. And so in a reflectron, they fly in, the ions fly in a little deeper if they have more energy. And as a result, we get time focusing and energy focusing, and we get a very, very high mass resolution. We get a very, very high mass resolution. The downside in this case is that in order to produce a field to do that, we need to have a mesh that's terminating the field. And obviously some ions might crash into the mesh and get lost. And so typically that's about half of the ions, because the ions need to fly in and back out again. And modern reflectrons also have a few meshes in between so that they can accommodate wide view angles. And so we lose a lot of ions, but we gain a lot of mass resolution. And our LEAP atom probe has such a reflectron, our home-built atom probe doesn't have. Okay, and with that, we'll end for the instrumentation, and next time we'll go into field application physics. And I'll just take you downstairs for a minute, and I'll show you what a detector looks like in reality.